मंत्रालय द्वारा भी जल शक्ति अभियान कैच द रेन भी शुरू किया जा रहा है। इस अभियान का मूल मंत्र है कैच द रेन वेयर इट फॉल्स व्हेन इट फॉल्स।
इस मूल मंत्र का अर्थ है घर का पानी घर में, खेत का पानी खेत में और गांव का पानी गांव में। हर नागरिक को शपथ लेनी है कि हम मिलकर वर्षा जल संचय की ओर काम करेंगे। सरकारी व गैर सरकारी भवनों पर रूफटॉप रेन वाटर हार्वेस्टिंग स्ट्रक्चर बनाएंगे। अपने घरों के आसपास पिट्स बनाएंगे ताकि बरसात का पानी आसानी से जमीन के नीचे एक्वाफायर तक पहुंच सके। मॉनसून आने से पहले नए चेक डैम्स, पॉन्ड्स, वाटर हार्वेस्टिंग स्ट्रक्चर्स इत्यादि बनवाएंगे। परंपरागत जल निकायों जैसे स्टेप वेल्स, वेटलैंड्स और नदियों को पुनर्जीवित व विकसित करेंगे। पुराने रूफटॉप रेन वाटर हार्वेस्टिंग स्ट्रक्चर्स, चेक डैम्स, पॉन्ड्स, वाटर बॉडीज और तालाबों की मरम्मत कराएंगे और अधिकाधिक पेड़ लगाएंगे। याद रखिए, ये सब काम मॉनसून आने से पहले करें तो हम तालाब, कुओं, बावड़ी जैसे नेचुरल कंटेनर्स को वर्षा जल का संग्रह करने के लिए तैयार रख सकते हैं। वर्षा जल संरक्षित होगा तो हमारा कल सुरक्षित होगा। तो आइए हम सब मिलकर आने वाले कल को खुशहाली की मुस्कुराहट दें और जल शक्ति अभियान कैच द रेन के साथ वर्षा जल संचय की शुरुआत करें।
A very good afternoon to everyone. I welcome you all in today's 14 Water Tech Talk being organized by National Water Mission, Ministry of Jal Shakti and supported by Water Digest. The topic of today's talk is application of artificial intelligence and digital twin technologies for water management. I welcome to Mr. Neeraj Swami, founder CEO, SCAT.ai. Now I would like to invite Shri G. Ashok Kumar, Additional Secretary and Mission Director, National Water Mission, Ministry of Jal Shakti, to kindly propose the opening address. Over to you, sir.
Good afternoon, everybody. Welcome to the 14th Water Tech Talk organized by the National Water Mission. As many of the enthusiastic participants regularly follow us know, this is a series of talks which National Water Mission had started since October 2020, where we thought of showcasing the cutting-edge technology in water sector. And there are a lot of research activities going on in the various aspects of water technology. And we thought that we should provide a platform for the leading technology providers in the world to showcase their work and showcase the advancements going on in different parts of the world. So today we have with us Dr. Neeraj Swami, avid technologist and innovator, who would bring in on his talk on application of artificial intelligence and digital twin technologies for water management. See, we are all aware of the artificial intelligence and machine learning process and all, but we have not spent too much time on how it can be used for the water management and the new concept of digital twin technology. He will talk about that, but I would like to take 2-3 minutes before handing over to Swami. Basically, I'm very happy that the Catch the Rain campaign, which the National Water Mission had taken up under the guidance of the Prime Minister, with the blessing of the Prime Minister, on the World Water Day, that is on 22nd March 2021, has been going on very well. We have almost 39 lakh structure. That's about 3.9 million structures, water harvesting structures, were either repaired or constructed the country, despite losing time for second wave of COVID, as well as for the intensive vaccination drive in between the electors were busy. So this is a phenomenal success for us. Almost 4 million structures being taken up, at a cost of about 60,000 crores in this short period of 5-6 months is very good, because never before probably so much of concentrated work had been taken place anywhere probably in the world on rainwater harvesting structures. And as they say, if your intentions are good, your irada theek hai, to God also will be very, very benevolent. So we had very good copious rainfall this time. So definitely with the large number of water harvesting structures which we have built in, and the copious rain we received, this time definitely our water table, a lot of water would have been captured and stored, and our water table have definitely increased. And looking at our dream of a Tangar Mukt Bharat probably would be realized. So along with that, our step of other three steps associated with the campaign was also going on well. One was tree afforestation. Nearly 37 crore trees have been planted or in the process of being planted in the different parts of the country. And the portal which we had developed, it is JSA CTR Jal Shakti Abhiyan Catch the Rain .MOWR, the Ministry of Water Resources, gov.in. So JSACTR.MOWR.gov.in has also been very proactive, very much visited by people. So this portal takes up data from the ground level and puts in the website for public consumption as well as for the analytical purposes. These the data in the of the works done in various parts of the country has also been put there. We are also put about 6 to 6.5 lakh photographs of the various work done. Again, a huge database to help transparency, and also to ensure that the works done are properly recorded and documented. That is also in our website. We also said that we'll have an enumeration of water bodies from the ground level, sort of a crowd sourcing of data. That's also happening. Almost 15-16 lakh water bodies data has been put on the website. Because unless we have good data, we cannot plan it. So good data requires some portal to put this information from the ground level. So this portal we have created where the information is made available, and also the scientific planning which we had envisaged at that time. We said that in the last 2 months or 3 months, we would also focus on developing scientific planning for the water conservation after the marking of the and geotagging of the water bodies. So a lot of water bodies or in the has been geotagged and information in the portal, and with the information available on the various water bodies and water harvesting structures, we are planning to go for scientific water conservation plans. I just been to Gurgaon. Haryana has done a wonderful job of creating information, a database of all the water bodies from the very small water bodies, 10 by 10 structure, large structures, water body data is available with them. And that will be used for analyzing the requirement of new water harvesting structures if they require, or also look at the health of the existing water bodies and where the requirements of repairs, etc. are there. That also will be done. So we are looking at a scientific data-driven water conservation plan. That is also a part of the Jal Shakti Abhiyan Catch the Rain campaign. We also said that we will have Jal Shakti Kendras in every district. A lot of Jal Shakti, more than 400 Jal Shakti Kendras also been set up in various parts of the country. Yes, the Jal Shakti Kendras would be one point data center or a data resource center or a guidance center for handling water resources in the district. That's also going on very well. So the first phase of this Jal Shakti Abhiyan Catch the Rain campaign, where we actually try to look at the construction of water body of the water harvesting structures and really literally catch the rain. That is getting over. Probably by end of this month, the monsoon, most of the states, the country would be over. Now, Chennai, as I speak now, a lot of rains happening in Chennai and southern parts of the country. So the retreating monsoon rains may be available for certain parts of the country for around 1 more month. So by and large, the monsoon is over. So the focus would be now shifting from catching the rain or the structures to be built to catch the rain to the scientific planning and also using analysis of the data which we get. That's where the application of artificial intelligence and digital twin technologies of water management comes in. Very appropriately, the topic, a new topic, because the digital twin concept itself is a new concept for many people. So it's like a digital modeling of various water bodies and various systems and how it functions using the software. That's a very novel concept. This is not much used in the water technology, so we can simulate floods, so we can find out how much water can where will be the submergence if this conditions is a what if conditions. All can be used to analyze and find out the effect of climate change on water, effect of floods on submergence of land, etc. A lot of things can be taken up with these digital twin technologies and artificial intelligence and machine learning processes are being applied for it. So, Mr. Dr. Swami is one of the pioneers in that field. He is an avid technologist and inventor, having deep interest in artificial intelligence, cognitive technology, and behavioral economics. And he founded the Green Sheen Environment Foundation to create the network of scalable impact. He has presented his papers in many fora, in many international fora, and he has been well received in many of the water technology summits. So he is keen to bridge the gap between impact and execution in the areas of sustainability, climate, healthcare, by leaning on strategic technology, lean innovation principles, and applied economics. So it's a combination of many things. He is currently serving as senior director for one of the world's largest conservation non-profit co-leading non-organization, and also co-leading the sustainability accelerator with Techstars and TNC, and acting as founding CEO of various ventures like Adaptric and SCAD AI. At Green Sheen, where foundation where he founded it, he serves as a voice for leveraging emerging technologies for piloting and scaling water, well-being, and climate science innovations at the intersection of the society and nature. Neeraj holds an honorary MBA from the University of Chicago, School of Business and Economics, Strategy and Entrepreneurship, and a bachelor's in science from Marquette University in computer engineering and mathematics. With a passion for wildlife, nature, and technology, he first witnessed the intricate relationship of health, nature, and people in the 8th grade at the Rural Education Volunteer Week for Water Pollution in Gujarat in India. So he has roots in India. He has been in US dealing with cutting technologies and not only in the technology field but also in the economics field. So you have a person who has a well-rounded personality, and I request Sri Neeraj Swami to deliver his talk. Swamiji, this is a very interesting platform because we get a lot of people niche. This is a very niche program of the National Water Mission. We get people from very, very renowned and technology institutions following us. Sometimes we get as high as 2.5 million views for our tech show. So there you are. Probably you'll be talking to a lot of people. A lot of people will be watching you. So over to you for your talk on artificial intelligence and application of artificial intelligence and digital technologies for water management. Over to you.
Thank you, sir. I really appreciate your introduction, and good afternoon, everybody. It's good to be speaking to this crowd. I've followed the mission for a while now, and I've spoken to G. Ashok Kumar sir a couple of times about things that relate to the topic we're going to go over. Water is a very interesting topic, not just because it is part of this conversation, but most importantly, it's a fluid natural resource. Unlike a natural resource like land or soil, water happens to be a dynamic one, which means data, AI, machine learning, technologies that can help us understand their management are going to be a full array of options. And I think if we're looking at a technical audience here, I think you'll appreciate the degree of innovation that can happen there. And it doesn't have to be global, it starts local. So I'm going to share my screen. I'll walk us through a few slides I've put together to introduce you to some of the concepts that we have leaned on, and that is an area that we can definitely explore. Let's see again. Okay. So we're going to talk about the application of artificial intelligence and digital twin technologies for water management today. Before I start, I'd like to look at a mental model when it comes to AI and digital twin technologies, specifically around natural resource management. And that model is called the adaptive management cycle. It's a way of thinking, you might be familiar, but to recap for those who are not, it is a way of thinking about how science turns into action, turns into measurement, and turns into insights, which allows us to drive change, make decisions, and do this as a cycle. And each part of that cycle allows us to have a feedback loop. And when there are feedback loops, we start from science that does a lot of planning with infrastructure teams. Do is the implementation stage. Think about what happens on the ground as you are bringing in technologies as well as bringing in facets to understand how this works. Monitoring stage, which is a place for you to see and understand whether your work is working, whether the natural resources are behaving the way they should. And learning, understanding what that data is telling us and assessing it with respect to the original plan we set forth to do. This is a repeating cycle. We don't seek perfection in the first go, and water is dynamic, nature is dynamic. It's a continuously evolving asset and a system. And when that's the case, your data is changing, the plans have to change, your assessment of the data, of the system is changing, and we need to accelerate how we learn from what has been done. And in order to do that, we lean on streaming data. We lean on a lot more data that comes into play. As G.S. Sukumar sir said, data is where everything starts. And we have to understand the opportunity that we have at hand by using and applying how this data can give us the insights needed to act. So let's look at a few realities of what happens when we try to model AI and machine learning using data that's available. First of all, it's time consuming and expensive. So we'll look at a couple of solutions in the marketplace that have helped us bypass this and focus entirely on the science. One example I tend to give more often than not is around the idea that our climate resources versus healthcare or talent, for instance, HR use cases, they do not tend to give you bad data. They just have noisy data. And that inherent noise is in the quality of the data, mostly not because of the fact that our planet or our natural resources are trying to tell us something different. If you ask somebody what and how do you feel, they give you, they don't necessarily give you a number. They say, I'm feeling good. And it's until you measure it, you don't know whether it's the body temperature good or it's just, feeling sluggish. But if you ask the planet how it's doing, it's going to give you a number. If you ask the water, what you're measuring about it, it's going to give you a number. And so when you combine good quality, high fidelity data with data science and apply it through subject matter expertise, the bigger headache becomes modeling, creating and deploying models that work. And so data science can be expensive and time consuming. When we look at prioritization and optimization, the planning phase, the learning phase of that image I had on the previous slide. When you look at the stages of planning, learning, any of those algorithms that are trying to help us prioritize and optimize rapidly and iteratively, they love fresh data, which means we need to be able to collect data at a faster rate. Geospatial satellites are one way, but there are other technologies that have emerged that help us address and collect more fresher data, more ad hoc data. Let's say there was a natural event that happened. Let's say there's a flood, or there's a drought, or there is some local, pollution event that has caused some water management challenge. How quickly can we assess the condition without having to rely entirely on manpower, and rely entirely on technologies that might not be always providing the most up-to-date and the fastest stream of data? And then there is another pillar where I believe AI and machine learning can really help us, is transfer learning. The idea that you can train a model or train an approach on a given data set that has been robustly crafted and transfer the learnings from that into a new problem, which is similar, not identical, to the existing problem, the one that has been addressed and solved. So I'll look at that and share a couple examples. And digital twins are one of the biggest areas of opportunity here. They sound like a big name and a big project, but you can start small with digital twins and scale them up. And so we'll go through some of those examples. One way of removing those gaps and addressing these opportunities is leaning on some newer trends of data. And all of this is in light of augmenting our science's superpowers, basically allowing us to take scientific insight and address it throughout the cycle of planning, implementing, monitoring, learning, repeat. The first area of opportunity we are seeing in the marketplace is with autonomous AI. The engines and platforms that take really high quality data and pure subject matter expertise and allow the cloud machines to basically take over and run those processes of model design, model experimentation at an exponential rate. What that really does is frees up precious scientist time, management time, and engineering time to really lean on compute to accelerate what models might exist. It's a good feasibility test that gives you some, close enough answer. This is not a game of seeking perfection, but it's a game of seeking progress. So if you're able to accelerate your path to understanding how technology or how data is telling you what it needs to, and use technologies such as autonomous AI, then it will actually help you to look at a couple of examples there. Accessing more data without breaking your bank. We don't need expensive satellites. We don't need expensive sensor networks, although they are very, very easy to procure. They have a high cost of management. So we've seen a technology called Near Space Labs. We'll look at them. They basically have created a technology that sits above the drone level and underneath the satellite level, and collecting images with some sensor information, especially in hyperlocal scenarios. And you can deploy these technologies, these camera balloons, in a matter of hours, not days. And then I think understanding, how systems change, as GSO Kumar sir said, there is a lot of opportunity in understanding systems with digital twins, but we've seen it in other ways. We've seen it in AR, augmented reality, mixed reality use cases. And now we're starting to see some extent of that apply in conservation and water management scenarios. So we'll look at a few examples. And what I'd love to leave you all with is an open question to think about digital twins and start exploring avenues where they might help your world and your work, and lean on how accessible they can be for everything that we're trying to do. Autonomous AI, like I said, helps accelerate your data science workflows. By leaning in on technologies like Data Robot and Big ML, you can actually delegate a lot of that heavy lifting back to the computer and focus entirely on the subject matter expertise, understanding, one, that the quality of data is of prime importance. So if you can focus, we don't have infinite time, we also don't have infinite energy. So if we can focus our time and energy on creating better data sets, the work that's being done by Water Digest, the team, and the work that can be done by all of us in crowdsourcing that data, high quality, high fidelity, trustworthy data, then you don't have to worry too much about the model behind it, because I think there are technologies, and I believe there's math mathematics that can actually accelerate that for us. So there is a model building software and experimentation software called DataRobot, and another one called BigML, both of which have great presence in other sectors like financial, understanding fraud data in banking transactions, understanding patterns of healthcare activity from patient data. Well, these are things that can apply to our work, especially in natural resource management, particularly with a dynamic resource like water. It's a transaction happening every second. There's a DataRobot really allows you to focus on raw data set and entirely in the quality and the fidelity of it. And it basically processes it in mass volume, going through an ensemble of models. So it will take existing models that it has built, it has trained. They have a data science team that is writing new models for specific use cases. What the software is doing is it is actually taking these raw image data sets, and you don't need to provide hundreds of thousands of images for certain classification tasks. I have seen and used this platform with 500 images of dried waterways versus roads, rural roads, and comparing what those images from satellites, which of those images in the satellite were of dried waterways versus roads, so that we can focus our work on areas where there have been dried rivers, as opposed to get confused by waterways, especially in surveyed land that has not been surveyed more accurately. That task took us a couple hundred images of each type, and maybe a day of working with a platform like DataRobot to come to an 85% accuracy model. Now, it doesn't say that human workforce is not needed for doing AI machine learning. I think our energy is better suited to go after better collecting quality data and understanding the feedback loop of whether our data is telling us any signal that's worth pursuing. Refinements and improvements can always be done with more manual workflows, but insight will come through this kind of automation. It's also very important to lean in on these tools and services and not trust black box AI. What I've seen in the marketplace and what I've seen in the space of conservation is, unfortunately, a lot of innovation comes with a magic potion that's sitting behind some black box that people do not want to explain and help us interpret. So it's one thing to automate model design, feature extraction, and ensemble testing, but the another layer of this whole advantage is to be doing that in a transparent, explainable way. So understanding how data moves through every layer of the model up until insight to a prediction layer. It's very important to have that aspect be available. So as you explain and as you explore some of these technologies and the work in this space, I think AI is, in my regards, is only as good as how explainable it can be. And that is something we have to pursue, because at the end of the day, these are solutions to scientific problems. And then scientific problems that are advising our management outcomes, management guidelines, prioritization. It's a full cycle based on science. Another platform that we've seen that's done really well, especially for unsupervised learning, is BigML. Similar kind of a tool, cloud-based platform. You basically have the focus of running all your preliminary data science activities on the cloud, and then automating some degree of cluster, anomaly detection, association, topic modeling, name it, any sort of deep nets, even basic regressions, which we've seen in cases of prediction. Sometimes linear regression, logistic regressions, basic machine learning, basic statistics can help a lot more than going after deep nets. You see everybody going after deep neural nets and deep learning nets. Not needed. You can get a pretty decent result with some basic statistics and start analyzing data science, especially making it very accessible. When you have good data, it's good to work on it, it's fun to work on it, but more importantly, it becomes easier to iterate on it. The second pillar that I was referring to is around the quality of data. Let's say we have, a water body we want to manage and understand that specific resource around, what are pollutants, surface pollutants, what is happening underneath the surface. There's ways to deploy sensor networks that can manage and understand that. And do that at scale can sometimes be challenging. But if there needs to be some spatial imagery that can capture high level, high degree of of fidelity in those images, then we really have to think about some newer tools and technologies. And here's a company called Near Space Labs. They started in catastrophe and calamity management, essentially helping understand what happens when there was an earthquake, for instance, or what happens when there was a degree of a natural event. And they are able to deploy these devices at that layer that's between, it's in the stratospheric balloon technology. It's near space. It's between 16,000 feet and 100,000 feet. And it sits in an area where there is enough room to understand the high fidelity of what is happening and manage some degree of hyperlocal weather conditions and plan it, because you can deploy it very quickly, and it doesn't have to be a drone, doesn't have to be manned. It is something that can be automated. They've created a really interesting technology, which we have used in conservation space in my work in the conservation industry, to really get rapid assessment of condition, especially when there has been a certain event. For instance, harmful algae blooms. These are events that happen in certain stagnant water bodies and lakes and ponds. And there can be algae blooms that can really cause a lot of damage to the local flora and fauna, but also affect the water quality downstream, especially if it is part of our consumption. And when that happens, how do you really assess and catch those conditions in early stage? You need better technology that can assess and measure and capture that data. And you can start using some of these tools to really apply images, capturing images, and then using image-based AI to understand condition in those specific regions. The whole power of this kind of technology is to really understanding what is going on at a very specific local level when you want it. So it doesn't have to be, it doesn't have to be once a week, which is usually, or once a day, which is usually when satellites can give you some of that insight. It really matters, to look at it at multiple times per day and drive different coverage, and doing it at a very, manageable cost. Because at the end of the day, we have to be mindful. If we are looking at this from a economic value perspective, then it has to meet the bank. Let me switch gears to a big part of this conversation, which is the digital twins. I start to look at digital twins from some of the more primitive, more basic, fundamental views into it, and then looking at some examples. And I'll leave you all with some thoughts on where you might be able to explore this work. Capturing all this data and making it very accessible is a good thing, not just for science, but for also citizen science. There's innovations in this space that we have explored and thought about. There's some work going on in Greensheen around using data that we capture and mixing it with reality through some form of a water coin, for instance. How do you incentivize actions? There has been focuses in the area of virtual reality and understanding a space without having to go there. Here's an example where this is actually in UK, where they basically used weather pollution and air pollution data to really build an app so that citizens could see in augmented reality. They hold up their phone wherever they're standing, and they can see how much actual pollution is there, because pollution is hard to see sometimes, especially when you live in places where traditionally there isn't a measure of that. This is an example where they have used real life streaming data and models that have been generated about pollution in a given region and overlaid that with real life scenarios. There's opportunity to do that. And you have data available, like the wonderful data sets that the Water Digest team have put together. You could really start incorporating those and mixing them into realities that help citizens understand. And you can also run training on people wanting to work in the water sector by giving them a context that ties it to real life. Data on a model, in a computer, on a screen, in a PowerPoint is one thing, but when you can see it embedded into your natural resources through a viewfinder, like our cameras on our phones, it becomes a lot more insightful. That brings me to digital twins and this idea that has been emerging in the conservation space. It's not new. It's been used quite heavily in infrastructure planning. Actually, Singapore was one of the first countries/cities and infrastructure systems that leaned on a digital twin to plan out most of its work. And that has been a great idea and a concept because it's manageable, but it's also been a lesson learned in understanding how this technology really works. For those who are not familiar, what it really is just what it sounds like. It's a digital twin. A digital twin is of a real world system. Anytime you have a complex world system, it doesn't have to be big systems. It can be small systems. It could be specific devices and specific entities. If you can model and understand its structure, the dynamics of how the structure changes and evolves over time, and what happens when various change effects drive interconnected behaviors. And so what that really means is you could digitally model a scenario or a system or a component and then understand the physics of it and understand how it is modifying over physical factors and other aspects. You can actually build off of that technology and understand and run faster models. Here's a resource image that I find particularly helpful. Slightly technical, but just ignore the technical layers on it and just understand the cyclic nature of what's really happening. You have a data management layer that interfaces with a decision-making system. There's two layers of models that interface with each other: a physics-based model that's understanding the system, a data-driven model that's understanding the dynamics. There's optimization. You could do some degree of planning activity, decision-making activity on that data based on the model processing, which then goes into a visualization planning tool, which ends up getting data from the actual emitters and actuators and sensors. And these are your technologies, IoT technologies, which are basically Internet of Things sensors. Imagine them as little sensors that are placed in various parts of the system that measure a certain aspect of a certain level of insights. And I see there's some background audio on the call here. Let me see if I can mute it so we can. Excellent. Thank you. All right. Let's see. So perfect. So yes, in that cycle of data collection and understanding how this becomes part of a model, you start understanding this in a digital twin format where you're able to kind of not just measure the system from its data sets, but you're starting to model it and use that in a cyclical nature to basically create a replica, a digital replica of a system. This has been used in water utilities. Here's an image from Esri. Esri is a ESRI, the leading GIS platform, Geospatial Information Systems platform, to help you visualize maps and information that is visual on a geotagged database. It's an opportunity for really helping us understanding how these various systems can be modeled by a set of data feeds, by a set of devices that measure and release and track those data feeds, and then build an entire stack of offerings on top of it. We've used it to understand expenditures. We've used it to understand planning activities, scenario planning. How can we understand performance, especially if it's a physics-based model? All of this through bringing various types of data into a central place called, a digital system, a digital twin. Some of the technologies that we've applied on this side to collect the data have been some of the tools that we've been looking at actually. The Near Space Labs, rapid assessment of collection of geospatial imagery, especially multiple times a day, helps us understand very minute differences in events and effects. We also have used a network of sensors, hydrological sensors, understanding quality of water, water condition, nutrient quality, temperature, things that are happening below the surface of water. We've also looked at technologies that have helped us understand more manual attributes, for instance, existing scientific models that people have created that are hypothetical scenarios. We use that as another data stream. You put all of that together and start modeling the system, you start understanding a digital twin. It doesn't have to look any which way. You're not building a virtual reality universe. It doesn't have to look and feel like that immersive. That makes for great marketing, but a lot of times digital twins can be literally collection of models that you're understanding and assessing. And to finally tell the story, you need a visualization tool. And that's when tools like Esri come into place that let you visualize your digital twin. Digital twins in the water sector, there's a company, Digital Waterworks, that has done some amazing work, and they have really outlined an entire process of how to go about it. And I'll share the resource here on the slides, and I'm happy to send these slides along to anybody that's interested. But really what they're doing is they're taking in existing physical infrastructure and putting it through a data funnel, as we've explained, as we've looked at. This is through various degree of resources. You have GIS, back office, all those IT data sets that take on some of the sensors, which is the operational insights of what's going on in those water infrastructure system. And then looking at other physical sensors like engineering technology sensors, like water quality, asset performance models, hydraulic data sensors, and you create a cognitive digital twin. What that really is modeling is a combination of all the assets, the data sets that are coming with, but also putting that in the structure of the system. You're not just building it in an isolated format. That gives you access to the data that's coming through. You're also combining with that some secondary models, and those secondary models help you understand a bunch of use cases. You can do capital planning. You can look at for operational maintenance. You can also look and work through the digital twin for emergency preparedness and response. This is the most intricate use case we've seen even in the conservation space, where we are looking at change management. With water management specifically, you are looking at not just operations, maintenance, capital planning, and emergency preparedness, but also looking at the opportunity to understand what interventions work and create almost like a hub or a much more accelerated learning cycle on intervention that addresses water management, especially as it impacts sustainability, as it impacts efficiency, as it impacts meeting certain goals that have been set for what we need to do to avoid the climate catastrophe we're all facing. So lots of opportunity here to really drive value, especially in the water sector. What I particularly think there's opportunity on in this area is because water is a dynamic asset, and you have an opportunity to collect a lot more data that is changing, fluid data, then you really can build on these digital twin technologies pretty robustly. We've seen that even, everything doesn't have to be this big system, right? I've said that before. It doesn't have to be a massive system, or you don't have to model an entire plant, water management site, although it would be amazing to see that. It can start with some of your high or critical components of the system and modeling them. Generators, understanding how certain pumps might be working in certain conditions. You might be able to see if you have a pollution retracting system, you can really start looking at water pollution retracting systems and management systems specific to a very specific need and a context, and build for that and understand how that system is going to interact. And you're really building a means of understanding a very expensive entity through software, so that you can play with the software and not have to incur expensive costs on that physical entity or that system. You can also do scenario modeling with software. You don't have to do that in the real world. You can look at what's the worst case, best case scenario and come up with a way to say, hey, if my solution is going to be somewhere between this worst case and the best case scenario, but it's closer to the best case scenario because of how my digital twin is performing, you can use that to help make a case for funding, make a case for support, get more science involved. It's again, information gives you insight gives you the ability to make better decisions, lower risk, lowering risk gives you rewards. So there is a lot of opportunity to really drive that funnel of information by leaning in on digital twins. And I use the word opportunity deliberately a lot because there is a ton of work going on in this space. However, when people talk about digital twins, they talk about this massive method of capturing insight and representing it in a digital model. But it really can be at any scale where a system needs to be represented in a digital format to run simulation. So it doesn't have to be compute related. It is based on how well you want to model some version of the real world and how much do you want to use that model for decision making. In the water management space specifically, again, this is from DHI. They have provided 3 different layers or ideas of how you might lean on digital twins. One is building digital twins to understand water process models. This is your physics and science data-driven models. If you have sensor data, if you have weather condition data, you can really start understanding how the water process, the actual hydrological process is working, especially in boundary conditions, in special weather conditions, understanding loads on the system. So you can build digital models, digital twins to understand water processing and water management, the process side of the aspect. The second one is an asset model. This is something that is a visualization. This allows you to understand dynamics from a visual standpoint. This is where imagery can really help. This is also where 3D modeling software can help. There's open source software. There is other tools. There are other tools that are available that you can lean in on. It is really helpful to lean on these models to build a visual layer into your digital twin. And then finally, you have a way of decision making based on what you have modeled. If you can nail 1 and 2, then the third stage is good data and good condition modeling is giving you a strong physics-based underlying structure that has been digitally modeled. Then you have an asset model understanding how those structures and the physics interact with your actual assets in a visual format. Again, that visual component doesn't have to be perfect, just something that gives you enough insight on understanding the various components. It can be a flat schematic. It doesn't have to be a 3D model. It can be a GIS schematic. It doesn't have to be a 3D globe model. Take those and start running benchmarks and metrics on them with additional science scenario planning. I think when we opened this call, GSO Kumar sir said, running scenarios, what if scenarios. I mean, there is a big opportunity here, especially when you get 1 and 2 right. And the work that's going out of Water Digest, I think there's data sets that we can lean on to start understanding the physics of it. With the work that's going on in technologies like the Esri software, open maps initiatives, there's a lot of work that's also being done in regional satellites that are capturing much more higher spatially configured imagery. We can lean on those assets to build a much more robust representation of it, which allows us to now get into planning, doing what if scenarios, decision making, understanding what might be times to schedule repairs, understanding downtime, even getting into very granular use cases of what happens if a certain part of this water management system breaks or is weak or is strained. How do you resource plan for that aspect? So with that in mind, I'd like to leave you all with just one thought and take on questions at this point. If you want to dive into anything deeper or talk about anything specific that I've mentioned or share your experiences, I'm happy to jump into those. But yes, just think about, what can you do when you have immense amount of high quality data, enough to give you insight on a physical model that you can represent and learn and engage with a digital twin. So tons of work happening in this space. Really appreciate this opportunity to tell, weave a little story and share where some of this work has been with you all. And thank you so much for this opportunity to share the story of where I believe the data from planning, implementing, measuring, learning can help us with water management.
Thank you, Neeraj. So it's a very interesting topic because the data-driven decision making has now come to India. But we are collecting a lot of data, but then, as you rightly said, unless you have good quality data, it will be of no use. So quality data collection is something which we are now striving very hard. We are, as I said, as part of the Jal Shakti Abhiyan, also trying to collect very fundamental data of the number of water bodies in the country, the extent, the quality of water available, etc., etc. That's also being collected. But we were also doing a lot of for the impact of climate change on water resources. We had been doing a lot of statistical downscaling and dynamic downscaling models using the GCM simulations in CMI P5 modeling was done. So these are all done with the professors of the IIT Mumbai and other technology institutions. The work is going on. But what I found was that sometimes were mentioning about not seeking perfection, but you are trying to make progress. But some of these modeling, which after many years of research and very large computer hours of working, they say that it's only 40% correct, 50% correct. So then that's where I feel sometimes, you have put so much of resources, so much of energy, and so much of computing powers into it, and then you come with a model with only 40% prediction. It's as good as a weatherman telling that this may rain today or may not rain today. I don't know how do you react to that, but probably this modeling may improve statistical downscaling and dynamic downscaling, which we were doing. One was that most of these were limited to certain areas of the country. So India being a very vast area, so some of the areas we were doing it in some maybe Gujarat basin, somewhere in Tapi basin, somewhere in southern India, somewhere in North India. So these are all small patches, and then stitching them together to get India centric model was getting difficult, because India being a very vast country, conditions are different in different parts of the country. So probably maybe that's why we are difficult to get a one country model for us, because various parts of the country, we have in the east western part, we have very low rainfall, and on the eastern part we have a lot of rainfall, and in some areas we have melting of snow, or the glacier melting happening. Somewhere else you have absolutely no snow, it's very hot. So these are the different scenarios in India. So, but in the last maybe decade or so, India had been facing a lot of problems with climate change. Your rainfall pattern has changed, intensity has changed, and today also it's raining very heavily in some of the part of the country. These are all very big patterns which are emerged, and somehow our scientists, I don't know whether they're able to predict or not. So this is where your digital twin modeling and artificial intelligence in what if scenario can be of help. So I'll leave it open to the questioners. So if you want to respond to this, you can respond to this, and we'll open it for the questions.
Absolutely. No, I think you made a very, very interesting point, volume of data and scale. I think we've share a story that I think applies to water management, and especially the scale of what India is, and the diversity of the water resources, regions, and why getting to that mythical one model that will understand all of water in India might be a risky one. We tried this in land management, land cover detection. So we understood, looking at land cover change, what happens over time when there is human development near protected lands, and how a certain region in Asia responds, and certain community in Asia, in Africa responds, and certain community in South America responds, is very different, even though the resource is the same. And so it was very difficult for us to model, create one change detection model entirely based on a homogeneous data set that was still captured across the same three regions I just mentioned, because there are human factors that are different. And that is where I believe that scale will come through a collection of very high fidelity network of solutions that have been understood in specific regions. And then to use a technology like digital twin to create a representation of the whole, as opposed to taking a representation of the whole and making a digital twin of that. So you start leaning in on, what is happening in a specific lake in a urban setting, what is happening to a water body in a fluid river setting, what is happening in a glacial situation. You start combining these various different scenarios, and that becomes your collective representation in the future. So I think with the high quality of data that you're collecting and where you're going with that, the opportunities to hyper localize and build very specific digital twins that first understand those local sites, and then creating a digital twin that connects all these various models into one ensemble representation, which is a big audacious goal. But I think the problem is this big right now, as we are facing with climate change. We absolutely need to lean on these these technologies. So I really appreciate your nudge in that direction. Thank you.
It's open for questions. Yeah.
Thank you so much. Thank you so much, sir. Before we proceed further, I would like to introduce the format of Q&A. If you have any query, kindly click on the raise your hand icon available on your screen, or else you can share your query with us in chat box too. So, sir, we got one query which is from Ms. Akansha Mehrotra, and her question is, how can digital twin technologies help overcome problems in areas with inadequate digital infrastructure?
A very good question, and that is where I think we have to understand that areas that don't have very strong digital infrastructure have the potential. Let me stop sharing. Excellent. Let me share it. Areas that don't have strong digital infrastructure, we have to look for sites that perform in a natural way, similarly to the area where you want to understand. And so instead of trying to incorporate digital infrastructure in a region that doesn't have that much, look for a similar site where there might be a lower cost way of getting that, or it also already has infrastructure, and model the digital twin there. So let it learn and understand the physical dynamics, the physical models, the hydrological models, whatever it is that you're trying to model in an area where you actually have control. You can actually build something. There is funding available. There might be local NGOs. There might be local private sector entities that want to support that work. And you basically learn from one area and then take that digital twin to an area where you know the physical conditions, but you cannot incorporate the technical infrastructure, and use the realities of this infrastructure deprived region to model and test and learn what if scenario planning on the digital twin you created. So what you're really doing is you're creating a representation of science from another place and running a what if analysis in another place. So that's one approach of going about it. You will not get a perfect solution, but you will get enough insights. You will get enough insights and value of what's going on. This has been used in rainforests, and this approach has been used in understanding rainforest conditions. The thicker the rainforest, the harder it is for people to go through and understand and collect data. There's so much greenery between the top of the canopy of a rainforest, especially look at Amazon, and what is happening on the ground floor, because there's so many layers of tree that you can't really get and collect data just from GIS. So they've trained models in areas where they can manage and understand, that data, that behavior, and created GIS represented digital twins by using sensors from places where they could actually put these devices. So they actually took a sample, a lab of a rainforest, modeled it, and now they take that and are measuring everything else in some of these bigger rainforests. So hopefully that is one way of going about it.
So another query is from Mr. Shaurath Gandhi, and the question is, do you think AI can fully recognize the diverse range of water problems faced by citizens across the country, like in India?
I think this will come to one of my first comments. A great question. And it's an ambitious one, because there is definitely an idea that general artificial intelligence that scales at the level of understanding everything and reasoning with everything is potentially possible, but it's very hard to really attain that. You really have to seek, before you seek an AI that can understand and help us model every single scenario in India, you have to understand the data that needs to go feed that. And the priority has to start with the data. How much can we do to collect better data? How much can we incentivize citizens to be a part of the solution? Right? And have them understand where the data is going to help not just us as scientists and practitioners and innovators, but them as citizens. And if you can create a relationship between citizens, data, and science, then you will eventually get to a place where you have a good ensemble. You're never going to get perfection, but you can get Pareto efficiency, the idea that 80%
of the problem can be solved by 20% of the effort. And that is something that we can really think about with better quality data. Good question, Aniket.
So next query is again related to the last one. Mr. Pawan Kumawat, question is how we can use the AI in metropolitan cities to very rural areas of our country and like African countries?
I think that's a very, very good question, because one big nuance that changes from metropolitan data sets to rural is people density. And when people density changes, your demand curve changes, the demand for natural resources changes. You also have a different relationship with nature. So what you can potentially do is, instead of trying to model everything that's happening in a metropolitan city using an AI to understand the overall picture, get more granular in the systemic components of the bigger system. So you could really look at AI that is understanding hydrological factors, predicting things like algae blooms on water bodies that have certain pollutant level. What happens when a certain specific water level changes? How is temperature and water level and nutrient quality affected? So you can build or take AI that has understood hydrological conditions or hydrological factors, for instance, or water flow, predicting how rainwater flows because of the physics that you can control in metropolitans, and apply that in rural settings and see what happens if this contour, this river in this specific area of this African, Saharan region. What happens if you can model flood or drought or rural water management because of your AI models that have understood the hydrological conditions in a much more controlled environment like the metropolis. So I wouldn't say the AI in the city is any more robust than the AI that could be generated in rural. It's more the transfer. The transfer would be at the more granular level, things you can understand about specific water conditions that might then help you understand change in other regions. So one opportunity.
Sir, how big of investment is required for implementation of AI technologies?
10 years ago, it was a lot more than 5 years ago. Today, it is a lot less than last 5 years ago. And it's because a lot of the challenge has moved to where the problem really exists: quality of data. Nowadays, you're also seeing, if you're doing work in the water management space or environmental space or conservation space, even research, the computation challenge, amount of compute power you need to basically run a model, build one and try it, is covered by some of the bigger cloud company technologies like Microsoft, Amazon, you know the names. And they often like to give away credits for you to try and build things. The challenge moves upstream. It moves towards data collection. So if you can have access to data through organizations and initiatives like the Water Digest, through crowdsourcing some of that data, you really have an opportunity to build some interesting models and get started with it. You also have to think about the fact that data science, I quote somebody who's been in the AI space and is originally from Chennai. His name is Sri Satish Ambati. He's CEO of H2O.ai, one of the largest data science firms. He talks about this term, says data science is a team sport. So I really think if you look at it as a team sport and not go about it solo, the cost will be less, the success will be greater, the learnings will be better, the data science will be better. So it's not that expensive to get started now, especially the sectors that you are looking at. And it really depends on the quality of data. So I would say make sure you have good data, otherwise you waste a lot of time, energy, and compute to get to a model that doesn't really say much.
So we are ending our Q&A session.
No,
here.
one more session, one more point. One of the problem which India faces is probably of water management. Basically, we have copious water, but water management. So demand water management is one thing very, very important for us. And if you look at it, the agriculture sector takes about 85 to 90% of the water. So in one of our water talk earlier, we had people from Israel coming in and talking about use of artificial intelligence in precision agriculture. So that means they used to calculate the requirement of water for each plant at each various time of its growth, its fruiting period or whether it's flowering period, and deliver the precise quantity of water at the precise location that means almost 100% water use efficiency. Now, this could be definitely a costly technology. So, have you come across this type of technology otherwise outside Israel, or is it being used in any other part of the world other than Israel?
I'll have to think this one through. I think there has been some work been done in Kenya as well as Tanzania around water demand management because of how there's two things. One is you need precision modeling, but you also need better survey data that is coming from that specific region. And the challenge becomes who governs that region, which is a really interesting challenge in parts of Africa. So we've seen some technologies that emerge there. It has been, going hyper local. So one solution fits all is something that we are not seeing a lot of promise in, at least in what we are seeing in the survey of water and natural resource technologies. So when you look at water management demand side, you are also looking at data sets that traditionally have never reached water management, and that's the socioeconomic data set. So start getting into some of those data sets. You have to have regional, hyper-regional, local presence, and a lot of manual surveying that needs to happen. So I'd be curious to see what Israel did. I know the model. I know the teams that have worked in Africa on some of these very hyper-local watershed demand management problems. What happens when a watershed upstream is managed and governed by a farming community and that downstreams into a city only a few kilometers down, and affects the overall ecosystem in a very dynamic fashion. We've seen some of that in Tanzania. And that is a hyper local demand understanding situation where we are taking the city's data and feeding it back to the farmers to help them understand how they should engage with the water resource before it even streams down, and using that model. But the amount of socioeconomic intervention that was needed in that facet, it became an education project as opposed to a science project. And so it's I think the problem opens up when you get into demand side, and this is where my economics hat comes in. I think it's more it's more driven by behaviors than science. So, but great question. Thank you, sir.
Thank you. Yeah.
Thank you, sir. And now I request again Mr. G. Ashok Kumar, sir, MD and Additional Secretary, National Water Mission, for his concluding remarks.
Yes, I think it was a wonderful talk. We were going through very uncharted territory so far. So thanks taking us to those uncharted parts so far, because in India we were actually not too much onto these data and data management and using, because it is probably a new thing which we are doing. So, but it's right. It's good that we learn the entire gamut of scope available, so that we can leapfrog the technology. You don't have to do the shorten the learning curve. You can shorten the learning curve and come to the most important destination rather than going through the entire process. So this is one thing which has been an eye opener for many of us, particularly in a country where now floods are happening very, very frequently, and climate change related issues are coming up very frequently. unprecedented rainfalls coming in unprecedented times, and the demand of people as also and the increase. They also would like to get information as much as possible, but forecasting rainfall, forecasting the rainfall pattern, forecasting what area would be submerged, which areas would be affected. All these things are now coming up. So probably that's where better water modeling has to be done. Climate prediction modeling has to be done. Still, we are grappling with what are the parameters. Many parameters probably are missing out because some of the predictions last year of also for the rains were not very accurate. Some agencies predicted it very well. Some agencies not predicted very well. And of course, things change as it goes on because the data with which they predict in probably in December may be getting changed because of the climatic conditions. Sometime in March, April, that really affects the rainfall pattern later on. So you can't blame the science which predicted it based on a particular set of data. So these are all something which is challenging. And but as I said, the acceptance that we need more data-driven decisions, we need to have better modeling patterns. It's coming through. It's a vector change. So thanks, Rich, for your wonderful presentation, and hopefully people who have followed it up would definitely just about, because this is actually, I said, it's a niche program. So it is actually meant for people who understand violence of science and technology, etc. I'm sure that they would have found it very, very interesting, and they would have definitely be in touch with you also, because we also get questions in the emails which we transfer to you in case we want. Once again, thank you for your wonderful presentation and your time for introducing us to a very simple and contemporary topic.
Thank you. I appreciate, and really, you have an amazing team that has put this together. So I will be an attendee in your future tech talks. This is very nice initiative. So thank you, sir.